Okay, let's try another example. So here I have a function that's equal to x squared y squared. Now this function might look simple on the outside, but let's check it out. So fx equals 2x y squared, and fy equals 2x squared y. I want to set them equal to 0. So now um, I could try doing that whole solving for one instead of the other, but I want to show you another technique. Another technique is to factor. So if you think like 2 times x times y squared and 2 times x squared times y equals 0 equals 0. And this technique works better when it's even more complicated. So then the top equation will be 0 if one of those terms is 0. The bottom equation will be 0 if one of those terms is 0. So there's really generally like when you have a situation like this, you have 4 different possibilities for getting a 0, 0. You have both of your first terms equal 0, and that way you get x equals 0. You could have both of your y terms equal 0. That you would get y equals 0. And then both of my cross terms are um, when x equals 0 and y equals 0. So this is a critical point. These are lines because we're in two-dimensional space. And so that creates some issues because now in this situation, I have infinite critical points. Okay? Infinite critical points because if I try to graph this, then it's 0 on the y-axis and on the x-axis. So um, let's see what we can do with these infinite critical points. So d equals, well, first we've got to calculate our second derivatives. So fxx equals 2y squared. Fyy equals 2x squared. Fxy equals 4xy. So then d equals 2y squared times 2x squared minus 4xy squared. So then that gives me 4x squared y squared minus 16x squared y squared, which is negative 12x squared y squared. This is 0 at all of my critical points. It's 0 at all the critical points, which means my second derivative test tells me absolutely nothing. So what do we do in a situation when the second derivative test fails, when it can't tell us anything? Well, in that case, look at the function. So let's go back to the original function. And if we look at it, then f of xy equals x squared y squared. Okay? So if I think about f of, say, like a 0 plus a little thing, I'll call it c1 plus, no, and then uh, like some value of y plus c2. Let's just call them c and d so we don't have subscripts. 0 plus c. So let me back up. So then a typical point of my critical points is something like 0y or x0 or when they're both 0. So this covers like looking at these for y in the real numbers for x in the real numbers. Okay, so my critical points look like in one of these sets. Okay, so then let's say, what if I take one of those points and go a small distance from it? So if I take my point, say 0y, and I go a small distance, CD, where C and D are very small, then I take my function of that. So f of, say, 0 plus c and y plus d is going to equal 0 plus c squared times y plus d squared. That's going to equal c squared times y plus d squared. And c is a small number but greater than 0. And d is a small number and smaller than whatever y is. So then this is going to be greater than 0. But f of 0y equals 0. And so then any point close to my critical point has to be bigger than it. Therefore, my critical point 0y is a minimum because any point close to it is bigger than it. Okay? So then that makes these guys are all minimums. And if you were to try to graph this, you'd get parabolas. If you hold like y equals to 1, you have a parabola. If you hold x equals 1, that's a parabola. If you hold x equals 2, it's a much steeper parabola. Hold y equals 2, it's a much steeper parabola. And so then the way to think about this function is that it's like parabolas and then steeper parabola, steeper parabola, parabola, steeper parabola, steeper parabola, and then parabola, steeper parabola, steeper parabola, parabola, steeper parabola, steeper parabola. So that's the best way to think of that. And so then that my x and y axis are all the minimums. Okay, so that's kind of a weird example, but there will be times when D fails you, when the second derivative test fails you. I want you to be ready for that.